All right, good afternoon, everybody. Let's get started. So welcome to 6004. Today we're going to continue our journey into combinational logic and actually start looking at the hardware description language that we're going to use in the labs and in the rest of the course. And so if you look back at what we've seen about combinational logic this far, you're now well prepared to, if I give you, a circuit that has few inputs and few outputs, you have the necessary tools to derive, a precise specification for it. You can use truth tables, you can use Boolean expressions, and then you can synthesize those into gates with the techniques that we saw in the previous lecture. However, that's not sufficient when we start looking at large circuits, right? Think about what would it take to derive the truth table for a circuit that has 64 1-bit inputs. How many entries would you have in that truth table? 2 to the 64, right? So probably not something you'd like to write. So today we're going to do two things. We're going to first learn how to design large combinational circuits by looking at 3 useful examples, looking at 3 basic circuits that you will use all over the place, an adder, in particular a ripple carry adder, a multiplexer, and a shifter, and specifically a barrel shifter, which is an efficient way to shift bits right and left. And then, while we do this, we're going to introduce this Minispec hardware description language by just learning how to implement these different combinational circuits in the language. And so at a high level, what we're going to do is design this combinational circuit as a function, as a Boolean function, which then, with this language, you'll be able to both automatically simulate and synthesize into gates to actually get a circuit from your description of the circuit. Okay, so let's start with the first major circuit we're going to see today, the combinational adder. So our goal is to build a circuit that takes 2 n-bit inputs, A and B, shown in orange and green here, and produces an n plus 1 bit output, S, that is the sum of A and B. Now, if A and B are n-bit inputs, the sum is at most going to have 1 extra bit, right? We'll do specific values of n, right? So we'll get a specific combinational circuit with some number of input wires, some number of output wires. But just one thing in terms of notation, when you start looking at large circuits, it gets kind of tedious to draw all the individual wires coming into the circuit and going out of the circuit, right? So we will often use this abbreviated notation where each input here describes a group or a bundle of wires, right? So you can see the difference here is that instead of having of n minus 1 to a0, we have a single value a, and then we have a thicker arrow here that has this slanted cross, or this slanted line with a number, right? And that denotes the number of wires that this group of wires represents, right? So this means an n bit or an n wire input. Okay, so again, if n is 32, it's going to be kind of unpleasant to design these by drawing or deriving the truth table, doing sums of products and so on, right? We very quickly run out of steam with these techniques that we saw last lecture. So instead what we're going to do is go back to the binary addition algorithm that we saw in lecture 1, right? And this is called the standard algorithm for addition. It's also called the elementary addition algorithm because it's what we learned in elementary school. And so remember, you have 2 numbers here in binary. You essentially at each step you add the 2 digits here and produce an output, and then you might produce some carry bit that is then added to the next column, right, in the next step. So in a more formal way, if you take these particular inputs, right, these particular values, this is 14, this is 7, this is 21, we've already seen this precise sequence. If instead of using these ones and zeros and these concrete values, we just express these as symbolic constants, right? If we wanted to do 4-bit addition, essentially we'd start by adding up A0 and B0 and getting outputs S0 and C1, and then in the next step we do C1 plus A1 plus B1, and we'd get output S1 and C2, which then we would use in the next step. Right? So in the ith step of this addition process, we have a fairly limited number of both inputs and outputs. Right? We take 3 1-bit inputs, 3 1-bit values, we add them up, and we produce a 2-bit output. Right? So in particular, if you look at I equals 2, we take C2, A2, B2, produce S2 and C3. In general, we take AI, BI, and CI, we produce SI and CI plus 1. Now, these carries, which we're denoting with C of I here, we're going to call them carry in for this one that we use as an input, and then carry out for the one that we produce as an output. Right? So we can say that we're producing a sum and a carry out bit, and we're taking in A, B, and a carry in as 1-bit inputs. Right? And this is just the binary sum of the 3 inputs. So now, given this, can you build me a circuit that performs this one particular function? Take 3 1-bit inputs and produce a 2-bit sum of the inputs with the techniques that we've seen so far. Yes, right? This is just 3 inputs. The truth table is going to be 8 terms. This is all going to be very, very reasonable. So then we're going to follow this approach to build another. Right? We're first going to build the circuit for adding these 3 1-bit numbers and producing a 2-bit output. This is called a full adder, and we're going to use this notation over here. So we get A and B inputs coming from the top, and then the carry in input coming in from the right, and then the outputs S comes down below, and C out comes down comes out of this left side. And this is drawn like that and not input to output, because now that we have this circuit, which we'll derive in a second, we can compose multiple of these circuits to do multi-bit addition. Right? So remember, this circuit does a single step. Right? Let's say that we wanted to do 4-bit addition. Right? Then we just use these 4 full adders in sequence. Right? The first this full adder over here takes A0, B0, a carry in, which we call C0, but we're going to set to 0 here because we just want to add A0 and B0, and then produces S0, C1, and then the next full adder takes C1, A1, B1, adds them up, produces S1 and C2. The next full adder takes C2, A2, and B2, and so on. Right? Is this clear? Is it clear that this circuit produces a 5-bit sum of 2 4-bit inputs? Okay. So the key strategy here, and this is what we're going to see over and over again, is that if you want to build large circuits, we'll basically divide and conquer. We'll first start building small circuits with the tools that we know, and then we'll just compose them to get larger and larger circuits. This design, by the way, is called a ripple carry adder. There are many kinds of adders. We'll see more complex adders next lecture. And this one is very simple, but it's actually quite slow. Can any one of you tell me why is it slow, or why I'm saying, this is probably we're going to want to build something faster? Yes?
Each full adder has to go through like the previous one before it can go through, so there's up 4 times the propagation delay.
Exactly. So the propagation delay is something that involves the full chain of the entire chain of full adders, right? So this means that as we increase the number of bits of the input, the delay of the circuit is going to increase linearly. And so if you have 30, 40 picoseconds per full adder, which doesn't sound like a lot, when you try to do 64-bit addition, now you're getting into nanoseconds, right? And that is too slow for current technology. And so we'll see some techniques to do this, to do addition faster in the next lecture. But for now, we're going to stick with this simple one. Okay, so now the only thing we have left is to derive the full adder, right? And we can do this with a truth table. We can write Boolean expressions. Let's start with the truth table. And so rather than just going and deriving everything, which you could, you have to, it's useful to realize that you're doing addition, right? This is a 2-bit number that represents the addition of these 3 1-bit values, right? So if I want to add up 3 zeros, what do I get at the output? What should my output be? Yeah, 0, 0, right? If I want to add 0, 0, and 1, what is my output? 2-bit output, 0, 1, yes. But not only this one is 0, 1, right? This one is also 0, 1 because there's a single 1. And this one is also a single 1, right? So 0, 1. How about if I want to add up 2 1s? What should I have at the output? 2, 0, 2, right? 1, 2. 1, 0, which is 2 in binary, right? And likewise, 1, 0, 1, 0. And finally, if my 3 bits are 1, then my output should be 1, 1, right? So that's the truth table right there. Okay, so now for the Boolean expressions, we can derive the Boolean expressions in a couple of different ways. The obvious thing, which we're not going to do in this lecture, but you can go ahead and do it, is to just write out the normal form of each of these, just from the truth table, translate it to a Boolean expression, and then try to simplify it. Right? This is exactly the procedure, the systematic procedure that we saw in the previous lecture. But let me just, there are some nice things about addition because it uses, each of these is a very well-known function. And so it's worth spending a minute just thinking about some compact ways of expressing these two operations. Right, so if you look at S, at only this bit S, right, can you tell me what function of these 3 inputs it is? Right, so S is 1 in all these cases, right? When you either have one single bit set, right? These 3 cases over here, or when you have all 3 bits set. In other words, S is 1 when the number of 1s in the input is odd. Exactly. So this is essentially the parity function. So we call this parity of A, B, and C. And you can again derive this from the truth table, but the parity can be done with the XOR function because the XOR function has 2 very nice properties. First of all, let's say that we wanted to compute the parity of just 2 1-bit values, right? A and B. Take a look, right? This is A XOR B, right? This symbol over here denotes XOR. And so if you have an even number of zeros here, right? Either 0 or 2, you have a 0. If you have an odd number of 1s, right? Sorry, if you have an even number of 1s, this is 0. If you have an odd number of 1s, right? Either 0, 1 or 1, 0, this is 1. So this is the parity. A XOR B is the parity of A and B, right? But we want the parity of 3 values, not 2. Now there's something really cute about XOR, right? Which is that the parity of this column is exactly the same as the parity of this column, right? Or these inputs, right? So this has an even number of 1s, 0, and this has an even number of 1s, 0. These 2 have an odd number of 1s, 1, and this output has an odd number of 1s, 1. This has an even number of 1s, 2, and this has an even number of 1s as well, 0. Right? So if we want, you see, because the parity of A and B is the same as the parity of A XOR B, we can just apply XOR again, right? And so the parity is just A XOR B XOR the carry in. And in general, you can just do a chain of XORs for the parity of an n-bit input, right? Okay, the carry out is also another famous function, which we call the majority function, right? Because the carry out is 1 when at least 2 out of the 3 bits are 1. And this, again, you can write this in the normal form, apply reduction a couple of times, and you'll get to the following expression, right, which is just A, B, A, C in. So A and B, or A and C in, or B and C in, right? And this is simply because we're just taking pairs, right, the 3 possible pairs of 2 inputs, and if any of those is true, then the output must be 1, right? Okay, any questions? Good. All right. So we're done, right? That's all we need. Well, except not quite, because we now have a very clear way to derive or to write the equations for the full adder. But if you actually want to describe a 32-bit adder, right, or something that's fairly large, a 256-bit adder, we don't really have the tools yet to do this properly, right? So you could use a truth table, but we've already said, truth tables grow exponentially with the number of bits of the input. So, for anything larger than 3 or 4 bits of input, this is not going to be good. We could write Boolean equations, right? So you could start saying S0 equals, 0 XOR A0 XOR B0, and C1 equals blah, 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 and then you'd end up with, 64 Boolean equations that are almost the same. So a lot of repetitive work, probably you don't want to do that. What else can we do? Well, we can realize that there's a recursion here, right? So we can make up some ad hoc notation for recursion, for recurrences, right? And so just say that for k going from 0 to 31, s of k, is this formula over here, and c of k plus 1 is this other formula over there. And yes, that will work here, but again, there's a lot of ad hoc notation, and it's not general. Finally, we can do what we've been doing so far. We can just draw the circuit, right? Problem is, when you're drawing something that has 10,000 gates and 30 different blocks, things get very hairy, right? It's very easy to make mistakes, to wire things to the wrong output. You have 30 wires crossing each other. It's very tedious. So in practice, what everybody does is instead we use a hardware description language. And a hardware description language is nothing else or nothing more than a programming language that is specialized for describing hardware rather than software. It is specialized for describing circuits that are then synthesized into gates, and we need a different language because if you think of something like Python, or Python or C, software programming languages are designed to be turned into sequences of assembly instructions that are going to be executed by a processor. And so we'll see that there are some subtle but important differences that make it very hard to use something like Python to describe hardware. And using a language, just like using a programming language gives you lots of nice advantages, has lots of good points, right? So we can precisely specify what we want our circuits to do. We can specify the behavior, and then we can use tools to automatically simulate them, to automatically synthesize them to gates, so that we get this high-level representation. We turn it into a bunch of gates. We send this to a company, and they build a chip for us. And we don't have to think about the particular gates that we have in this circuit. very useful when your design has 5 billion gates, as it is the case with some circuits today. Also, and this is quite important for the 6-3s among you, this enables us to build hardware with the same principles that we use to build software. Right? So we're going to be building up reusable functions, reusable building blocks, and then we're going to compose to get larger circuits, get things that are more complex. And the same issues are going to show up: modularity, clean interfaces. So you're going to use the same skill set. And finally, we get to have a familiar syntax, right? We can have functions, we can have variables, we can even have things like control flow statements. And this one is both good and bad. It's good because I'll show you a function, and barring some syntax issues that some things might be unfamiliar in terms of the syntax, but once you get accustomed to the syntax, you'll just read it like a program, right? And it will be very obvious what it's doing. Unfortunately, the dark side of this is that you can become confused and start thinking that you're writing software. You will write extremely bad hardware if you write it like you're writing software, because some things look similar, but they're quite different. And so what we're going to do throughout this lecture and the next one is actually focus on the concepts of how are HDLs different from programming languages. And when you're writing something like a function call, or when you're writing something like a conditional statement, what does that turn into? What circuit are you generating? What circuit are you expressing, right? And this is a general issue with all hardware description languages. The syntax is sort of the same, but never forget that you're writing hardware, not software. Okay, so with that, let's dive into Minispec, which is a simple hardware description language created just for you, based on BlueSpec, which is another hardware description language that uses a syntax that's itself based on System Verilog, which is the industry standard. So the syntax may look a little bit weird at first. In fact, it's something that you're going to see a similar syntax if you ever pick up any other hardware description language. So the high-level point is that combinational logic, we're going to describe combinational circuits as functions. I mean, this is not very surprising, given that we said that we need a functional specification, right? And that combinational logic, a combinational circuit, must have its output be precisely described as a Boolean function of its inputs, right? So here's one very, very simple function that implements an inverter, right? And so, there are different syntax elements here. Function name, and the return type, and the input arguments, and statements, and so on. And so we could go and do this description, but instead I'm just going to show you a demo. And by the way, there's a Jupyter Hub instance that you can all use to learn the syntax of the language, right? And there are tutorials on the website that you can all use. What I want to do instead is start with Python, right? What is going to go wrong when you try to compile this thing? Well, this thing has auto-highlighting, and you can see that the only thing that's highlighted correctly is this return statement here, so obviously this is not going to work. It's not going to work, first of all, because comments are not written like this. Comments are written C-style, so this thing is just telling us line 1 that's you cannot do that. Okay, so now we do this, but on line 2 we get this error, mismatch input def. It's basically saying, look, in Python you write functions with def, but here I'm expecting one of these other things, right? One of which is function. Well, we're trying to write a function, that's probably it, right? Yeah, hey, it gets highlighted. Probably that's right. Cool, except now we get another error. So here in inf, it's saying missing type of module or module name. And this brings us to one of the basic differences between Python and Minispec. Minispec is a strongly typed language. Everything has a type. And so you need to tell me, what does this function return? What type does this function return? Right, in Python you could pass anything that has the not operation defined as x and get the not operation applied here. But we want something that takes a fixed number of bits and has a very fixed representation. right? And so in this case, we're going to use the Bool type, which is the simplest type, which describes a Boolean value that can either be true or false. And you need to specify Bool for everything, right? So you have the function name, which is inv, and then the arguments. This takes a single argument x, which again we need to declare as type Bool. Now, if we keep going, it says mismatch input colon. Okay, expected either semicolon or equals. Let's try semicolon. And then, hey, we're now in line 4. Missing semicolon before return, yes. So like C and like many other languages, we actually need to separate statements with semicolons. Okay, so now if we try to compile these, it says extraneous input, end of file, expected another statement or end function. I see, so basically we need to terminate the functions with this end function keyword, right? So everything between function, the function line and end function is statements that describe the function. Okay, and we're almost done, except that, remember how I told you that everything was Bool? We also need to declare result as Bool. And finally, no errors found. So we have a valid minispec function, and as promised, you can synthesize this and get an actual drawing of your circuit. Yes, it's an inverter. Cool. Okay. So, fine. Not very interesting, but at least you get the hang of the syntax. You can also evaluate a function. So yes, you know, if you do inv of true, hopefully this will return false. Yes. All right. So that's it for the basics of syntax. There's a lot of things to unpack here, and if you're not familiar with C especially, you might find it a little bit hard to get going. But again, once you become familiar with the basics, this is very consistent. So again, all values have a fixed type, and also capitalization is important here. So all types begin with uppercase, all variable and function names begin with lowercase. So as I mentioned, everything has a type. We need to describe a couple of different types. The one that we've already started seeing is Bool. So values of type Bool can either be true or false. And you have just a few operations that you can do with Boolean values, right? So you can do Boolean not, which is this exclamation sign here. You can do Boolean and, which is these two and signs. Don't do a single and sign, that's a different kind of and, as we'll see in a second. And Boolean or, which is two different ors, two vertical bars. You also have equality and inequality. We don't have XOR or XNOR, but you know, if two Boolean values are different, that's the XOR, right? So if I write A not equals to B, that is equivalent to A XOR B. That's why we don't have specific XOR or XNOR operations. And so, you know, just let me give you a sense of a slightly more complex function that uses this, right? And so this is the majority function that we've seen before, right? It takes 3 Boolean inputs, and then it produces the majority output, right? So if we compile this, you know, it's just this same formula here. And again, we can go and synthesize it, and now we'll get something that's perhaps not quite what you expect, right? So it's going to be very important, I'm going to emphasize this a lot. You must be able to look at a function implementation and translate it to gates manually. So if you were to translate this function to gates, you'd say, well, we're going to need 3 AND gates because we're doing 3 ANDs, right? And 2 OR gates because we're doing 2 ORs. But again, this is an optimizing synthesis tool, and so you're getting something with 4 NAND gates. NAND gates turn out to be the fastest to input gate, and then 2 inverters. So it actually has 6 gates, but they're simpler, and you know, we're not going to get too much into the weeds of how that translation happens exactly. As I said in the previous lecture, there's a lot of algorithmic complexity into getting, you know, the smallest delay here. Okay, so Booleans are fine, but we very soon run out of steam, right? In theory, Booleans are pretty much everything you need to describe functions or combinational circuits. Everything else is a convenience. Everything that we're going to see from now on, you can do just with Booleans. And the first thing that we need to address is that, working with circuits that have a lot of inputs and outputs, it's kind of tedious to do with Booleans, because Booleans encode just a single bit. And so to solve this, we have a slightly more complex type that we call bit n that represents an n-bit value. Now, this notation is a little bit weird, right? It's bit hash parenthesis, open parenthesis, n, close parenthesis. This n is what we call a parameter, and we will see exactly how you can define your own parametric types and parametric functions in the next lecture. But for now, you can treat this as something where you plop in a particular number and you get a number that's that many bits wide. So we have several basic operations that we don't have with Booleans. We have bitwise logical operations. So these work just like the bitwise logical operations that we saw in RISC-V, right? Just like the AND instruction performs the AND of every bit of its two input values and puts the result in the output. Here, this code is defining a 4-bit input, a 4-bit value A, which is 4-bit binary value 0011, and B is 4-bit binary value 0101. And I could have written here A equals 3 and B equals 5, but I actually want to show you the numbers in binary because that makes it very obvious what the output is going to be. In fact, these 4 numbers have all possible combinations of zeros and ones. So for example, if you look at A and B, right, if we compute A and B, what are we going to get? Well, we're going to get 0 and 0, so 0, 0 and 1, so 0, 1 and 0, 0, and 1 and 1, 1, right? So 0, 0, 0, 1. Okay, any questions so far? Good. So the next thing that we can do is select bits from this bit n type. So for example, we can select a single bit. This returns a bit 1 or a 1-bit quantity. And in this particular expression is selecting A0. So A is a 4-bit value. We're selecting bit 0, which is this one. Now something that will completely confuse you if you're accustomed to lists, right, is that this is bit 0, this is bit 1, this is bit 2, this is bit 3. Bits go right, are enumerated right to left. Right to left, not left to right. If I was writing a list of things, I would enumerate things left to right. But remember, we're talking about numbers, right? And so numbers, we enumerate from the least significant bit to the most significant bit. So again, when you're dealing with bit n values, it's important to remember that rule, right to left. You can also take a slice of values or a range of values, right? So this is selecting bits A3 through A1, both inclusive. So again, this is slightly different from Python. This includes A1. And so this is 3-bit quantity 001 because we are selecting 0, 0, and 1. Okay? And finally, we can also concatenate bits, right? So we can say C equals open curly brace A comma B, close this curly brace, and we'll get 0011, 0101, right? So an 8-bit value consisting of the concatenation of both. Okay, questions? So there are many other operations that bit supports, and we're going to use none of them for now, because you can actually add, you can write A plus B, and you can even write A times B. And the problem is that we want you to understand what an addition actually is before you get to write A plus B, because that generates a ton of logic that you actually don't really understand how it works. And so for the next couple of labs, you're absolutely disallowed to use anything that's not this. And we'll check. All right, so now we have all the tools that we need to build our ripple carry adder and to write it in Minispec. Let's get started. So we can get started with the full adder, right? We can very directly translate the Boolean equations to this this function over here, right? So this function takes 3 inputs, 3 1-bit inputs, A, B, and C in. A, B, and C in, produces a 2-bit output that is S, that is the concatenation of C out and S, right? So how do we write S? Well, we can just write a statement where we define a bit 1 variable s, that is a, XOR b, XOR c in, right? We just XOR all our inputs. Remember that this sign here is XOR. And then for c out, same thing, right? We just encode our majority function there. Now, remember the difference with Booleans and with this is that here we're using bitwise logical operations. So before we had 2 vertical bars and 2 unsigns. Not here, because these are bit 1 values. So we're using bitwise logical operations, not Boolean operations. And finally, the only thing left to do is to just concatenate the value and return the 2-bit output, right? Okay, any question? Yes?
Can we concatenate Bool values?
That is a great question. No. So, in fact, this is a very annoying difference between Minispec and in general any hardware description language and software programming languages. So you have bool and you have bit 1, and they're both 1 bit very clearly, but you can't just assign a bool to a bit 1. We're going to ask you to convert everything explicitly. The reason is that these sort of explicit type conversions are a bit more verbose, but they reduce the number of bugs. If you're shipping out a chip that takes $100 million to build, you probably want to get it right the first time. And so you'll see that in general these languages tend to be a bit more verbose at the expense of, just to reduce the number of mistakes. Okay, so now that we have our full adder, let's build a 2-bit ripple carry adder. Okay, so this is going to produce a 3-bit output, right? So bit 3 is the return type, and then we take 2-bit inputs A and B, and 1 bit of carrying. So we just need to wire things up, right? So the first thing that I'm going to do is call this full adder function that we just defined with arguments A0, B0, and C in. And I'm going to get a 2-bit quantity, a 2-bit result that I'm going to call lower. Now this, if you look at the wiring diagram, this is the 0th bit of lower, and this is the bit 1 lower, right? So now what I need to do is create this second full adder, which I'm going to wire as follows, right? I want to take inputs A1, B1, and lower 1, right? The carry out of the previous full adder. So I am chaining them. And I'm going to get upper 1 and upper 0 as outputs. And then what do I need to return? Well, a 3-bit quantity that is upper 1, upper 0, lower 0, right? So that is upper and lower 0, the concatenation of both. Okay, there's something actually very crucial here, which is that we just called a function. And if you're thinking, oh my god, is there a stack? Are there registers? What is the calling convention? There's none of that here, okay? Functions are just in line. Functions are simply a mechanism for you to be able to reuse a circuit into other circuits, right? So each function call is simply creating a different copy of the circuit. You're not reusing the same circuit, you're not jumping to any definition, you're just creating a new copy of the circuit in your larger circuit and wiring it the way you specify. It is really important that you understand this difference, because otherwise you can get very confused as to what is actually going on in your function, right? Functions are just circuits. Then we can keep building things up and build our 4-bit ripple carry adder from 2-bit ripple carry adders, right? So same strategy. We wire up 2 RCA2 circuits, lower and upper. We take the upper bit of the first RCA2 and then feed it into the second one. And what do we return? Well, the 2 lower bits of this lower and then the entire upper output. So you can keep going, right? Do RCA8, RCA16, RCA32. It's kind of tedious though. We just redid the exact same procedure. right? So this, yes, we're gonna build larger circuits this way, but if you had to write a 256-bit adder, this would get kind of tedious. So next lecture, we're gonna see a way to write an n-bit adder for any value of n in a single function. Okay, so we'll pick this up next lecture. But before, for the rest of the lecture, let's look at the two other circuits that I mentioned. The first one is a multiplexer. Multiplexers essentially select between multiple inputs, select one output based on some select signal. The simplest one that you can have is a two-way multiplexer, which selects between two input values A and B based on the value of a one-bit signal S, the select input. So this is, in fact, nothing else than the Boolean function that we saw in the previous lecture all over the place, right? Y equals A and not S or B and S. And it has this implementation over here, right? It's just this set of gates. And this is just for one-bit inputs. If A and B were n bits, then you'd have this structure replicated n times. Right? You just have n copies of this in parallel, all of them driven by the same one-bit select signal. Okay, is this clear? Good. So we have something that selects among two things. We can have multiplexers that select more inputs, right? So a four-way multiplexer, instead of two inputs, has four data inputs, and then it has a two-bit select signal that can be 0, 1, 2, or 3, and we're going to select one of these inputs as an output and propagate it to the output. So this is one possible implementation. In fact, sort of the most straightforward implementation of this four-way mux is to just do it with three two-way muxes, with a tree of three two-way muxes, right? This first wave of two-way muxes is driven by the lowest bit of S, and then this one is the upper bit, right? And in general, if you have an n-way multiplexer, you can have 32-way multiplexer. You can implement this with a tree, with a deeper tree of n-1 muxes. Okay, so how do we describe multiplexers in Minispec? We have what we call conditional expressions. And so a two-way mux is a conditional operator, or what we call a ternary operator. It has the following syntax: S question mark B colon A. It basically says, if S is true, pick B, or this expression evaluates to B, otherwise it evaluates to A. And in this case, true is treated as 1, and so this must be a Boolean value, not a bit 1. True is treated as 1, and false is treated as 0. If you know C, or if you know some other programming languages, they use this exact same syntax, but Python, which is the language that you might be more familiar with, doesn't use that. It uses this other syntax for the conditional operator. B if S else A. So they're exactly the same thing. How about an n-way mux? Well, for those, you could do this with a very deeply nested chain of conditional operators, but that gets tedious. So instead we have a case expression that essentially lists all the possible values, right? And then looks at S, and depending on what S evaluates to, it selects the appropriate branch of the case statement. Now this particular S is a 2-bit value, right? And that's why it can go from 0 to 3. Okay. Now, here's something extremely important. If in a software programming language I write S is foo of X, or bar of Y, what is going to happen? Well, you're running this in some sequential stream of instructions, so the code is going to evaluate S, and then it's going to either execute foo of X or bar of Y, right? This is what we call conditional execution. Now, why do we do this? Well, because these functions may take a lot of instructions, and so why evaluate both, right? This is not at all how the circuit is going to synthesize, right? If you're doing this in hardware, here's what's going to happen. You're going to instantiate foo. You're going to give it x. Actually, just 1, 0. You're going to create a copy of bar. Right? You're going to give it y. And then you're going to select using s. It's really important that you understand this difference. Both foo and bar are created, are evaluated. They're evaluated in parallel, right? But they're both there. So when you have like a very deeply nested chain of expressions, you need to realize that you're actually creating a lot of hardware. You're not just evaluating one function. You know, if you have a case expression that takes 1 out of 32 functions, you actually have hardware for the 32 functions that you're calling. Okay, so with that, selecting a wire, actually, if you're doing a static selection, obviously this is just a wire. But if you're doing a dynamic selector, right, if you want to select a particular value, you can write x of I. And if x is a 4-bit value, you'll have a 4-way max, right, where you're selecting between the bits of the input. So maxes can also be used for dynamic bit selection. Finally, we get to shifts. So shifts are actually extremely easy if they have a fixed size. Just like bit selection is extremely easy if you have a fixed size. So let's say that we want to do a logical right shift by 2 of this 4-bit value A, B, C, D. The only thing we need to do is wire up things like this, right? So that we insert 2 zeros in bits 3 and 2, and then bit 3 becomes bit 1, bit 2 becomes bit 0, and bits C and D, the lower order bits are dropped, right? So this is just wires. There's no logic here. Right? For example, if we had 1, 0, 0, 1, and we shifted right by 2, then we'd end up with 0, 0, 1, 0. And arithmetic shifts, remember that we have in RISC-V, we have SRL, SRA. So this is the same thing, except that remember that we copy the most significant bit over, right? And this is useful for division by powers of 2 of numbers that are negative, right? So if we start with 1, 0, 0, 0, which is minus 8, and we shift right arithmetic by 2, we end up with 1, 1, 1, 0, which is minus 2 in 2's complement representation. But what about if we want to shift by some variable amount, right? So suppose that we want to build a shifter that right shifts a value by n, and n is anywhere between 0 and 31. It's some input. Now the obvious thing that we can do is say, well, we know how to do fixed sized shifts, so let's just do 32 of those, and then have a 32-way max to select among them. My question to you is this expensive? Right? Is this going to be a lot of logic or not a lot of logic? I mean, after all of these are just wires, right? So it can't be that bad. Well, how many 2-way 1-bit maxes are needed to implement this 32-way 32-bit max? How many input wires does this thing have, right? 32 times 32, 1024 bits. That's a lot of wires. That's a ton of wires. And so remember, we can do a tree of n-1 maxes, right, to implement an n-way multiplexer. So a 32-way multiplexer would be 31 2-way maxes, and then we replicate this, so times 32. So we'd have 31 times 32, which is about 1,000, in general, n times n-1. This is super expensive, right? So we're going to stop here, and then in the next lecture we'll see how to actually do this efficiently with what we call a barrel shifter, which is essentially just a cascade of conditional shifts by essentially by powers of 2 values. And we'll see that in just a logarithmic number of steps we can actually get this done very, very efficiently. All right. Thank you.